Hello students, in this video I would like to discuss a very interesting topic called infinite sequence. I would like to begin this discussion with a very formal definition of infinite sequence followed by its notation and set of interesting remarks. I am going to then give you a couple of examples to compute few terms of infinite sequence. And then we will try to focus our attention on a very special type of sequence known as geometric sequence. This particular sequence has many applications in the real world, and you are going to see at least one application today in today's lecture, and then in the coming lecture we are going to see some more application. All right, so let's try to start with basic definition of infinite sequence. What is infinite sequence? A list of numbers or spatial objects is called sequence. Right, so sequence is really the list of numbers or spatial objects. Remember, for us this list is infinite list. There are three different ways to denote sequence. Here is the set of notation. Because it's a list of number, you can tag them as a first term, second term, third term, fourth term, so on and so forth. Alright, so this is a formal set of notation: first term, second term, third term, so on, nth term. Or you can write your sequence in this format: ai with I running from 1 to infinity. Now remember, plugging I equal to 1 gives you your first term. Plugging I equal to 2 gives you the second term. Plugging I equal to 5 gives you the fifth term. Plugging I equal to 1000 gives you 1000 term. Right? And here is the third notation. We just write our sequence in form of an. Right? Without loss of generality, we assume that n starts with 1. Not all sequences starts with index 1. I'll give you some example, but again, if nothing is given, we will try to start our sequence with n equal to 1. Okay, so we have definition of a sequence with a set of three different notations. All right, as I said, I would like to give you 6 interesting remarks now. The first remark is about the name of two spatial numbers. I would like to give this number a1 a name, and I would like to give this number an a name. Alright, a1 is called the first term of the sequence. Alright, because it appears at the first position, I'm gonna call it the first term. It is a very useful term for us. Likewise, an is called the nth term or general term of the sequence. The wording that I am going to use frequently is the general term. Alright, so be sure you know when I use the word general term, I really mean an. Okay, now what is the importance of the general term? I want you to notice that one of my notation is in form of an, alright, in form of general term. So if general term is known, we can calculate any given term of the sequence. Alright, so if general term is known, then I can calculate any term of my sequence. For example, if I want to calculate 100th term, I just need to substitute n equal to 100. If I need to compute 50th term, I would substitute n equal to 50. Right? So it's that simple. Now, as I mentioned, that if nothing is given, we will assume that our sequence starts with index n equal to 1. Alright, so that is our fourth remark. Without loss of generality, we can assume that our sequence starts with n equal to 1. I also made a comment that not all sequences start with index 1. Let me give you one illustration here in the remark number 5. Suppose I ask you to consider the sequence an, which is square root of n minus 3. Remember, this sequence starts with index n equal to 3. Alright, again, a very interesting example. Remember, square root is something that we can calculate only for non-negative input. To make sure the input is non-negative, we need to consider n value starting from 3 or more, right? If n value is less than 3, then that means I am going to have negative entry under square root, and this is not a real number. All right, so this is the sequence that starts with index 3. So n equal to 3 will give you your first term, n equal to 4 gives you the second term of this sequence, so on and so forth. All right, so in some special cases, sequences, they do start with different index, but if nothing is said, we'll try to start our sequence starting with index 1. Okay, unless we have an issue like number 5. Okay, now remark number 6 is also a very interesting remark. It says the following, that not all sequences can be expressed in terms of an. Not all sequences can be expressed in terms of general term an. Alright, let me give you one example, a very simple and trivial example. For example, consider a sequence representing the population of world on 1st of January each year starting from year 1700. Alright, so the first term in your sequence is population of the world on 1st of January in year 1700. Second term will be population of the world on 1st of January in 1701. Then third term population in 1702, so on and so forth. It is very clear to understand that the population of the world is a random entry. There is no general term that can predict the value of this sequence for any n value. Alright, so we cannot really come up with a general term an which tells us what will be the population of the world in 2025, 2030 or 2050. Right, so obviously there are sequences that cannot be expressed in terms of a general term. Alright, so sequence may contain some random terms, and these random terms may make situation very tricky for us to handle. Alright, so as I said, this is really a formal idea about infinite sequences. Unfortunately, there are many type of sequences exist, and if you have sequence with random entries, highly likely we will not be able to write that sequence in terms of an. As far as this course is concerned, you guys are going to deal with nice type of sequences, right? There are many different type of sequences exist in the world. We are going to focus on one very special type of sequence. Right, so let me give you a couple of examples of infinite sequence that is based on remark number 3. If general term is given, you can calculate any term you want for the given sequence. Alright, so consider the sequence whose general term is 3n plus 1. Alright, what I want you guys to do is compute the first 5 terms of an. This is a simple deal. There is no trick. Plug n equal to 1, 2, 3, 4 and 5 and calculate first 5 terms of an. And then I want you to compute 100th term and 1001th term of this sequence. Intention is very clear that I want you to plug n equal to 100 to compute 100th term and n equal to 1001 to compute 1001th term. Alright, plugging n equal to 1 gives me 3 times 1 plus 1, which is 4. Plugging n equal to 2 gives me the second term, which is 3 times 2 plus 1, and that's 7. Plugging a equal to 3 gives me 3 times 3 plus 1, which is 10. A equal to 4 gives me the fourth term, which is 13. A equal to 5 gives me the fifth term, which is 16. And then I can compute 100th term by plugging n equal to 100, which gives me 301, and then 1001th term will be 3004. Alright, so as I said, Examples are super simple. It's just a plain computation, nothing tricky. All right. You guys should have seen, if you remember, you have seen something similar in the very first week of this course. Remember the theory of function, right? If I give you a function f of x equal to 3x plus 1, and I ask you to evaluate f of 1, f of 2, f of 3, f of 4, f of 5, f at 100 and f at 1001, you will realize that I'm really converting, I'm really asking you the same question in terms of function. Very easy to construct. These are, even though the discrete term, this theory runs parallel to the theory of function, right? So this is really like evaluation of a function type of question. The only difference here is over there the input was really the entry in the domain of your function. Here our inputs are natural numbers. Okay, all right. Here is the second example, very similar to the first one. For an equal to square root of n plus n minus 1, I want you to compute the top 5 terms of an, and then I want you to compute 49th and 100th term of this sequence. All right. Convince yourself that this sequence starts with n equal to 5, right? So the first term will be 5 minus 5, which is 0. So sequence starts with index 5. Second term will be square root of 6 minus 5, which is 1. Third term, square root of 7 minus 5, which is square root 2. Fourth term, square root of 8 minus 5, which is square root of 3. Fifth term is square root of 9 minus 5, which is square root of 4, and we know square root of 4 is 2. We can compute square root of 49, right? Remember what is 49th term? 49th term will have index 49 plus 5, which is 54. So 54 minus 5, that gives me square root of 49. This is 7. And 100th term will have, entry 101 plus 5. All right, so this starts with index 5, right? So 100th entry will have index 105. Square root of 10, slightly tricky, but understand that it's something that is doable.